and thank you everyone for being here. So there's been a switch in the room, so if you're looking for the security session, it's in G2. Well, here in G1, it's the Multicluster Toolbox. So multi-cluster. Some of you may wonder why anyone would need multiple clusters. Dealing with one is hard enough. But if you're in this room, you probably have an idea. And this question has been answered multiple times. So today I won't be focusing so much on the why, but rather on the how we solve multi-cluster problems. So just picture multiple teams working with multiple clouds, multiple data centers, in multiple regions. Problems are bound to happen. So the tools I will introduce in this talk are lessons learned from months of research at Admiralty, a company I founded to research this domain space and offer solutions. But I won't talk about those products in this talk. So why not just use KubeFed? KubeFed, for those of you who don't know, is the new name of the Federation V2 project. They renamed the repository last week. In some situations, it's a very valid response. It's a yes, if your use case matches. So what does Federation V2 solve? It solves a problem where you have a central cluster and you want to do top-down resource declaration. So you want to define declaratively your resources across your federation from one cluster. And you can do that by decomposing your problem into templates. That is, basically, you want to deploy, for example, a deployment here into multiple clusters with this basic template. And then you define placement, which is a list of cluster names or cluster selector, because clusters are custom resources in Federation. And authorize if you want some variations. So in this example, there are just more replicas in cluster 2 than in cluster 1. But not all multi-cluster problems can be solved with federation. There are plenty of application examples of multi-cluster. We don't have time to go through this list and discuss it, but feel free to give it a look, read them, and I'm sure some of these will resonate with some of you. But there are no off-the-shelf solutions to solve these problems. The tools are missing. But what kind of tools? What are we trying to build? So just like to build a shelf, you need some tools. And well, you know you want to build a shelf, but do you know what you want to build when you think about multi-cluster? And what I think we need is just like controllers are solutions to many problems in Kubernetes. That's how Kubernetes works. We need multi-cluster controllers. And so what is missing to create multi-cluster controllers is a way to watch and reconcile resources in different clusters. Say you have a high-level API in one cluster and some either Kubernetes or other custom APIs in another, and I want to reconcile them. But then if I delete an object in one cluster, I want the dependent resources to be deleted in the other cluster, and we don't have garbage collection across clusters. And finally, if you've tried a few multi-cluster solutions out there, it's usually pretty difficult to set up. You need to generate kube configs and store them in secrets, load them, or there's a custom CLI that you have to use and run an imperative command. And so it'd be nice if there was declarative bootstrapping for those things. So the generalized solutions to these problems are packaged in some of Admiralty's open source projects like Multicluster Controller and Multicluster-Service-Account. Multicluster Controller is, in a way, sort of a multi-cluster version of the controller runtime project, which is an official Kubernetes project that basically drives kube builder or the operator SDK. And a multi-cluster service account is a way to, as a system of controllers that imports and auto-mounts service accounts from other clusters into pods of a local cluster. But actually, we won't see a lot of multi-cluster controller in this talk. I thought it would be more instructive if we built a multi-cluster controller from scratch. And so we're going to start with the sample controller project. Some of you are familiar with it. It's sort of like an example project that you can use. You can fork it, vendor it, and create your own controller from it. What does it do? So it's an example, right? So there's a higher level API in this project that's called foo. And when you create a foo object, then a Nginx server deployment is created with some parameters. And so some people like to have higher level APIs for their users so that they don't have to figure out all the details of how to deploy this thing. Yeah, so let's try it. So there will be some live coding, live demonstration, and I don't want to waste your time. So I'm going to do a lot of copy pasting. I'm also a shameless slow typer. So before you can create a foo object, you have to declare a custom resource. And for that, there's a custom resource definition. Is this big enough for people in the back? So, yes? Okay, I'll try one like this. And so this is a very simple custom resource definition that has nothing of the advanced features that you should use, like validation and other things. So, but we don't need that for the purpose of this talk. So we're going to create it in cluster 1. Oh, for information, I just tested them before this demo. I've created 3 clusters in GKE that I'm going to use for the purpose of this talk. And they're associated with cluster 0, cluster 1, and cluster 2 context in my kubeconfig. And I also extracted individual kubeconfig files in a specific folder as a convenience. You'll see why. So I'm in cluster 1. I create the CRD. And then, so I checked out the code. I made just a few tweaks. It's really very, very similar to sample controller in master in origin. And so, yeah, I just added a plugin for GCP login, things like that. So this controller is running in another terminal. I can create a foo object, which is this one. It's just an example. The Nginx deployment will be called example foo, and we'll have 1 replica. Let's see if the deployment was created. Yes. What does it look like? It's an Nginx deployment. And we can update it with 2 replicas. And you can see that the deployment has been updated. There are now 2 replicas. And the usual, the usual controller loops thing. So when you delete the deployment, you want it to be recreated because the foo object still exists. That means as a user, you want constantly to be a deployment with the same name. So if something deletes that deployment, it should be recreated. It's nice also to, in a control loop, to update the status of the owning resource. And so here in the foo object, we see that there are indeed 2 available replicas. And it's also nice for the user to broadcast events. And so in the sample controller project, there are events that are broadcasted when there are errors or the sync loop was successful. And finally, if you delete the owning object, which is the foo object, you want the deployment to disappear, to be deleted. That is using garbage collection. All right, so we want to transform this sample controller project and make it multi-cluster. So I'm going to start by changing a few things and basically watching foo in one cluster and deployments in another cluster. And at the same time, I'm kind of combining a few steps here. I also, in this example, I want all those Nginx deployments to be deployed in the same namespace in that different cluster. I don't want the namespaces to match. It makes sense in a single cluster to want to the owner-dependent relationships to only exist within a single namespace, but across clusters, not necessarily. So that I can deploy that foo object, which could be, like, oh, I need a database, and that database is so I'm in a cluster in AKS, and I want a database, but my software needs DynamoDB, and so I declare foo, and so in the other cluster, we can deploy in cluster 0 here, we deploy all those common resources, central resources, from like this. And at the end of this talk, there will be a second step where we can define and declare those foo resources from any cluster. They're all connected to cluster 0, and cluster 0 runs all those dependencies in the same namespace. But if we want to do that, we have to understand how a controller works. And so this is a diagram from the sample controller project's documentation. It was actually originally published in CloudArc's blog, and so it was nice of DevData to contribute it to the project, and because it's a great way to explain controllers. So how does a controller work in just a few minutes? Usually create a set of informers, indexers, and reflector. So like one informer, indexer, reflector from a factory. You create one. Yeah, there's one created per resource. They can be shared if you have multiple controllers running in the same process so that's the way to optimize API calls. And so the reflector just lists and watches objects from the Kubernetes API, which are Kubernetes verbs, and the informer listens to those changes, caches the objects in using the indexer, so that all the gets and lists that you need to use in your code are optimized. They don't always call the API. They use the cache. And your controller can subscribe to changes, and that's what a controller does. And the controller sees some change, like a deployment was created, a foo object was updated, anything deleted, and queues a key in a work queue. That key is what we call the reconcile key. And it's important to have the same key for the objects that you need to reconcile. So usually in a single cluster, what we do is that we define the key as namespace plus name. That is a unique way to identify an object in Kubernetes. And so if we want to reconcile a foo object with a dependent deployment object, so with foo, we just say, OK, let's take your namespace and your name. That's your key. With a deployment, we need to know what the owner's name and namespace are. And for that, we can rely on owner references. And so an owner reference is an identification of the owner. Here, a foo object called example foo, and a unique identifier. Note that there is no namespace in here because in Kubernetes, we assume that owner-dependent relationships only exist in namespaces. Yeah, and finally, we process the items. And so here's where you put your business logic. It actually often looks the same. It's the usual control loop where you have a key. For that key, namespace name, you get the owning object in this case. That's a very common pattern for higher level APIs. And so you get the foo object, It's possible that it doesn't exist anymore, because in the meantime it was deleted. Between the time it was a change was noticed and the time the controller processes the key in the work queue, it's possible it's disappeared. Well, garbage collection will take care of the deployment. We're good. But if we find the foo object, we need to make sure that it has a deployment. So if we don't find the deployment, it means it needs to be created. So here is it could mean that the deployment has been deleted. It could mean that it's never been created yet. We actually don't really care because this is a level-based algorithm. We care about the current state of the world and what we want it to be. And so if we find it, it has to be up to date. If not, we update it. In any case, it's a good practice to update the status of the owning object and broadcast some events. So yeah, let's try to change sample controller to do this, like have deployments created in a different cluster in the foo namespace all the time. So I'm going to check out a code change. I will push this branch to a repository after the talk, so you guys can redo the same things on your own if you want. Oh, I already built it. Sorry. So built the manager to the current state. Let's see what I did here in the code. I won't go into too many details, but down so many changes actually. So in this first change, I was a little naive. May have broken things. We'll see. And so I just this controller, this manager has a kubeconfig flag to be run out of cluster, and so I just added one, which I used to create a different Kubernetes configuration in code. And I used that configuration to create a client and an Informer factory. And in the controller, I just replaced everywhere we needed to create a deployment, update a deployment, delete. No, we don't delete because we rely on garbage collection. Anytime we need to do things with deployments, I replaced using the foo namespace with a constant, the foo namespace instead. And that's it. That's all I did. Let's see if it works. I said I wouldn't waste your time. And what just happened? All right, so see if the next step works. With my kubeconfig. All right. Never mind.
The keynote doors are now open.
I'm gonna
Please make your way to hall 6.
say my messages first, and we'll try to go back to it a little later. So this had worked. It actually wouldn't work properly. Like I'm just not able to run it, but I should be able to run it. And what so in the example that hopefully you can do later, or we can do later. You create a foo object, and wow, there is a deployment in the foo namespace in the other cluster, so you're happy. But a few things don't work. For example, events are not broadcasted. When you delete the deployment in the foo namespace, it is not recreated. And if you delete the foo object, the deployment is not deleted, so garbage collection doesn't work. And the way to figure out what the owner is of a deployment doesn't work either. And so to fix that, we need to enhance the owner reference. The owner reference only provides information about the name of an object, but it should also, in our case, for multi-cluster, say what namespace in the other cluster, what namespace the owner is in, and also what cluster. In this case, we still have just one cluster that contains the foo objects. And the next step, we need another enhancement. And garbage collection doesn't work. So why does garbage collection not work? So let's step back a little bit. There are 3 modes of deletion in Kubernetes, which are either orphan the dependents, so you just leave them be. Say, if I delete the owning object foo, I want to keep the deployment in place, but just remove the owner reference, orphan it. Or you want cascading deletion, which is if I delete the foo object, my intention is to also delete the deployment. And so this can be done either in the background or in the foreground, and that is done by the garbage collection controller. The garbage collection controller is a generic Kubernetes controller that maintains a graph of owner-dependent relationships. And when it detects that, so it listens to basically all resources, and when, say, a foo object is deleted, it will check the dependency graph and see that, that deployment needs to be deleted. I'll delete it. And so that can be done in the background. So when you delete foo, it disappears right away. And the deployment is deleted just a few seconds later or immediately. It depends how fast your cluster runs. Or in the foreground. So how does that work? It uses finalizers. So in the foreground, when you want to delete in the foreground, that means you don't want the owning object, the foo object in our case, to disappear until all of its dependents, just the deployment, have been deleted as well. And so the garbage collection controller does that by adding a finalizer to an owning resource when it's deleted. This example is actually a deployment. If you deleted a deployment, you would want the replica set to be deleted as well and cascading to the pods. And so when you delete the deployment, deletion timestamp is added, but also a foreground deletion. And when the garbage collection controller is done, deleting all the dependents, it removes the finalizer and finally deletes the owning object. Well, problem in our case is that we have two clusters. Each has its own garbage collection controller, and they don't agree. They basically each have their own representation of owner-dependent relationships, and only in their own clusters. They don't communicate. So they're unable, they don't know what a multi-cluster owner reference is. So we could, and I'm actually working on one, create a multi-cluster garbage collection controller that is generic, and we could have a multi-cluster owner reference that actually is something that exists in multi-cluster controller. But the solution in this example is actually what I call poor man's in-controller garbage collection using finalizers. Basically, in our control loop, we're going to add a finalizer right when the object is created, and before any of its dependents are created, to avoid any race condition. If a foo exists, it cannot have dependents unless it has a finalizer. That way, when we delete the foo object, we'll be sure to delete manually, or like, not manually, automatically in our control loop, but like custom code, delete the dependence before we remove the finalizer. So this is in our sync handler in the controller, we implement basically a decision tree based on observations. So is the foo object terminating? Does it have a deletion timestamp? If it doesn't, that means it's still alive. And first things first, make sure it has a finalizer. And then go back to our control loop from the very beginning. Is the deployment found? No, create it. Is it up to date? No, update it. Things like that. For clarity, I didn't loop back with update status, broadcast events, but you still need that. So if it's terminating so kind of typically at the end of the life cycle, but remember that the life cycle is not the same thing as your logic in your sync handler, because we're edge-based. We're level-based, not edge-based. And so if a deployment is found, we need to delete it if the foo object is terminating. And if not, well, that means we're ready to remove the finalizer. We do that, and then we can just rely on our single cluster garbage collection controller to remove the foo object. In this second example, I added a cluster to the mix. So like I said earlier. And so this example should work better because I'm running it in cluster. The first example was running out of cluster from my laptop using kubeconfig files. One of them apparently has been tampered with. So in this example, I will deploy a pod in a cluster 0. This is where we want to run our controller. And we want to run it, in this example, in the central cluster 0. And we want it to watch all the clusters 1, 2, however many you want, and see if when they create foo object, make sure that we create the deployments that they need. So how does a pod call the Kubernetes API of its own cluster first? Well, it has a service account. When you create a service account, the service account controller creates a secret in the same namespace with a token to call the API. And the token is auto-mounted in the pod when it is admitted. And Kubernetes clients, like the Client Go library, know how to load the token file that has been mounted as a volume. And so all is good. Now, you can extract actually the token from that secret and create an equivalent kubeconfig file. And that is what people usually do when they do multi-cluster things. So you take that token, you put it here in the user, and then you take the Kubernetes API of that cluster and add some like names to know where to find things, and then store that in a secret. So it's a bit of a pain, but it works. So here is an example of an installation procedure for Istio multicluster with VPN connectivity. And so run all these bash scripts and extract that, extract this, create that. It works, but it's a pain point, I believe. So what I suggest is a declarative way to do this, to import a service account from another cluster. And so multi-cluster service account comes with a CRD called service account import. And a service account import is simply a cluster name, namespace, and name of a service account. And multi-cluster service account controller takes care of finding that secret in the other cluster, importing it, And then if your namespace enables it, at admission, pods that are annotated with those service account import names will see those tokens as kubeconfig files auto-mounted in a known folder, so that then your Kubernetes client library, like client Go, or I think the Python library does that, although maybe I shouldn't say that because I haven't used it, but most Kubernetes client libraries know how to use kubeconfig files because that's what you use in development when you're just dealing with your clusters that you created. And so you can just use your code as usual. But wait, some of you may think, how does multi-cluster service account import those tokens from the other clusters, right? Well, it's a chicken and egg problem. You got to start somewhere. And so I believe that if you install multi-cluster service account, you do that bootstrapping process once with a custom CLI. But then all of your other multi-cluster controllers can use the declarative API of the service account import so that you don't have to do that ever again. So it probably wasn't the rooster or the unfertilized eggs, by the way. Let's try a demo of that. So I'm going to check out my code, add a different tag, and basically because it just adds an example, and I'm going to deploy those stacks. And so I have a cluster N stack and a cluster 0 stack. What's in cluster 1 and cluster 2? We have a custom resource definition for foo objects. We do create a foo namespace, even though it will not contain any deployments. It's just a way to host a service account that is allowed to list, watch, get, update the foo objects, and create events. And it's, so there is the RBAC rules for that. In cluster 0, which is our central cluster in this example, we have a namespace that will host all the Nginx deployments. And a service account that is allowed to list, watch, get, create those deployments. Some binding for that. And then here are 2 service account imports to import that other service account from all the dependent, federated, as a general term, clusters. And finally, a very simple deployments for the controller that is annotated so I can import those service accounts. And then a way to, I just call with the same arguments that I used in the previous demo. So kubeconfig, get it from this folder where Admiralty service account import usually puts tokens. OK, yeah, it's almost done. It's actually a good thing that first demo didn't work, because we wouldn't have had time for this. So I applied those stacks to cluster 1, cluster 2 for cluster N. Then I'm installing a multi-cluster service account in cluster 0. And I'm bootstrapping with a custom CLI, cluster 1, cluster 2. These 2 steps, you should only do them for your first multi-cluster setup. If you create more multi-cluster controllers, you don't have to do this. Your clusters are already well known to each other, and they can import tokens from each other. So once it's bootstrapped, I can finally install the multi-cluster controller in cluster 0. I create the example foo in cluster 1 and a different example called bar in cluster 2. In cluster 0, you can see that our deployments have been created. That's it for the demo. So in short, we created this custom multi-cluster controller system using cross-cluster control loops, cross-cluster garbage collection, and declarative bootstrapping, which are the common ingredients at the core of these projects. There are many examples, and I'd be curious to hear about yours, because there's just so many things we need to do with multiple clusters. And so here's how you can connect with me if you want, and some links to the different projects I've talked about, either from Admiralty, multicluster controller, service account, and scheduler, which I actually barely mentioned. It solves 2 of the things in that list of examples, and then some of the official projects that I mentioned too. Yeah, and if we have time for questions, I'll be happy to answer a few. Thank you.